It's an honor to be presenting at the International Conference on Advanced Material Science and Engineering. Just like any other researcher in the field of technical ceramics and powder metallurgy, we love sintering, and so the temptation for climbing to ultra-high temperatures is just in our blood.
Ever since we started our sintering experiments, there was a single problem which kept limiting us in terms of the capacity to fulfill our sintering dreams. And that was the temperature limit of approximately 1700 degrees Celsius due to the type of furnaces usually available in most labs. And it was not having the right equipment for reaching to temperatures over 2000 Celsius. It was also interesting to see that a few of our colleagues who had access to ultra-high temperature furnaces had another problem. And that was the fear of doing experiments which could potentially damage the hot zone components, simply because these equipment are just a little bit too expensive. And for that reason, experiments done with such furnaces in most labs are too scientifically conservative, and the equipment are not used at all if there is a chance of a corrosive atmosphere evolution, as is the case in many liquid phase sintering experiments.
We really wanted to see the magical temperatures of 2000 degrees Celsius and above on our PID. So we started requesting quotations from a few companies who specialize in such systems. And to say the least, the prices were just too much for the budget that we had for sintering experiments. So we started to play around with the idea of building our own furnace back in 2012. And after experimental trials, which mostly proceeded as a hobby, we now have a magnificent furnace up and running since 2015, which is capable of reaching 2500 degrees Celsius with a hot zone cost of just $100. It has also become one of our best lab partners, proven to be quite reliable and a great tool for research on sintering of material which require temperatures in excess of 2000 Celsius.
We have had so much fun with it that we thought there are surely many other researchers like us who may be interested in bringing together a furnace using equipment which most labs have laying around here and there, in order to move forward with a furnace design which is too inexpensive to worry about its longevity, even if the experiments are rather damaging to the hot zone components. The immense possibilities that metallurgy and material science offer must be explored, and this necessity requires the ability to do experiments without the fear of an experiment's cost.
When it comes to material selection for the hot zone, there are only a few options available which can fulfill the requirements we have discussed, both in terms of cost and material properties. Therefore, we proceeded with graphite due to its impressively high mechanical strength at high temperatures, low vapor pressure, ability to withstand temperatures up to 3000 degrees Celsius, ease of availability, low cost, and rather simple machinability. There are very interesting graphite hot zone designs either published in academic literature or patented, some of which are widely used industrially. However, upon reviewing them in detail, we found that there are only a limited number of hot zone designs available that meet the requirements of a compact lab-scale graphite furnace for research and development purposes.
It is noteworthy that the majority of available designs require utilization of step-down transformers with ampere ratings of over 1000 amps, thus increasing the primary cost of the furnace as well as the cost associated with replacing and repairing of the hot zone due to the geometrical setup of the graphite heating elements used and in the available designs.
An additional problem with graphite furnaces is the difficulty in quenching operations, which tends to be solved through rather operationally inconvenient procedures, such as high inert gas purging as in the case of silica fiber drawing furnaces, making it rather challenging to quench a sample in vacuum. So with these points in mind, we proceeded with the following design criteria for the furnace.
The ability to reach 2500 degrees Celsius in just minutes.
Capacity to sustain the mentioned temperature for several hundred hours if necessary. The ability to cool down the furnace at very high rates without using any fluids for quenching purposes.
And most importantly, maintaining the cost of the main hot zone as low as possible.
We decided that the total current utilized should be less than 200 amperes and it must be operational on single-phase alternating current with the intention of minimizing the cost of the step-down transformer and other electrical components necessary for the system. So we tried a series of different designs which were simulated by finite element analysis, and it was concluded that the optimized geometrical design shown here is particularly interesting for a number of reasons, such as the ability to provide a higher total power dissipation by the heating element in comparison to a cylindrical or polygonal hot zone of the same volume, considering a constant surface loading value on both cases, which facilitates approaching higher temperatures and also extending the longevity of the heating element.
Moreover, every cubic centimeter of high purity graphite which has been sintered at elevated temperatures using hot isostatic press technology is very precious. So it is only logical to minimize the consumed graphite during machining of the geometry required. Therefore, in the proposed design, it is possible to simply machine slabs of graphite and to conduct them using nuts and bolts made from the same grade of graphite, minimizing the wastage during the manufacturing process. It is also noteworthy that a similar volume of hot zone constructed in the conventional cylindrical or polygonal designs consumes a significantly greater amount of raw material.
Our thermoelectrical simulations on various graphite grades have shown that it is possible to achieve a temperature of 2,500 degrees Celsius with an approximate power of just 2,000 watts for a usable hot zone volume of approximately 200 cubic centimeters.
Furthermore, the temperature variations within the central 60 cubic centimeter of the hot zone does not exceed 0.5% of the maximum furnace temperature. The mentioned values have been repeatedly confirmed experimentally.
The entire system works on single-phase alternating current, with the hot zone placed inside an ordinary vacuum chamber with two water-cooled electrical feed-throughs connected to a stainless steel chamber. And the entire system is practically consuming a power equivalent to 3 toasters. Another beauty of this design is that due to its size, the water cooling system has the capacity to cool it down very effectively if the power is disconnected. And we have seen an average cooling rate of approximately 300 Celsius per minute from 2,500 to 1,000 Celsius.
On a different note, one should consider the thermodynamics of a system in which any sintering or heat treatment is to be conducted. It must be very clearly analyzed prior to any experimental work, as the furnace design in itself can have significant impact on the chemical equilibria which emerges and also possesses the capacity to alter the phase equilibrium in solid state.
Therefore, we have done thermochemical simulations of the natural equilibrium of gases in the furnace in absence of any forced gas flow, because even under such conditions, the thermochemical equilibrium as a result of Baudouin reaction can quickly become dominant in a graphite furnace, either in vacuum or inert atmospheres. The molar fraction of gases which emerge under 1 atmosphere total pressure are shown here. And it should also be noted that carbon monoxide's partial pressure cannot be ignored, regardless of the process in question. It should also be considered that the equilibrium partial pressure of oxygen in such a system is pressure dependent. Therefore, the choice of vacuum level or positive atmosphere's total pressure should be taken into account prior to experimentation with such a system. Special attention should be given to furnace atmospheres as a result of residual gases during a sintering or heat treatment operation, since this factor can have a very significant influence on microstructural evolution and defect chemistry of the material being researched.
So to conclude, every one of us researching in the field of ultra-high temperature materials, especially on refractory metals and their carbides, nitrides or borides, can build a graphite furnace capable of reaching temperatures up to 2,500 degrees Celsius by bringing together the equipment usually available in most labs and a hot zone of just $100 with the service life of several hundred hours, paving the way for lots and lots of high temperature experiments.
With the only limit being our creativity. We are extremely grateful to our dear professors who have been a beacon of hope and inspiration, especially Professor Zohal Er at Physics Department, Professor Mustafa Urgen and Professor Servet Timur at Metallurgical and Materials Engineering Department of Istanbul Technical University.
Thank you once again.
Thank you for giving us your time. We will be looking forward to any comments or questions you may have.